We are Group 18 presenting our final redesign of the kitchen food processor. The kitchen food processor is a tool that slices food using a motorized blade, speeding up the process of prepping food while cooking. The production volume is around 1 million units per year, and total revenue exceeds $500 million annually and is growing year to year. We identified two target customers, the primary being individuals who cook often at home, and the secondary group as small food operations like food trucks and family-owned restaurants.
Here's an exploded view of our chosen product. Our product consists of 29 components excluding fasteners. Here's the fast diagram for a food processor, and it has one main functive branch, which is to mix ingredients.
Shown below is a function component mapping matrix for the food processor, which shows which components perform which functions. This shows which components are the most important, and therefore should be looked at first for redesign. As one can see, the food bowl, top blade, bottom blade, the food pusher, and the chute lock, as well as the food chute insert, perform the most functions. However, as discussed later, the top and bottom blades will be looked at for redesign first.
We then constructed an FDT based on the needs of home cooks, food trucks, and restaurants. Many functions will stay the same, however, the speed needs to be increased for the trucks and restaurants who have to serve customers quickly. Using this information, we made a CCT. All of the components in the speed column of the FCMM from earlier will be considered modules. Changing the blade assembly seems to be the most effective and should increase the speed while keeping the redesign costs lower compared to changing the motor, for example. An example module is the blade assembly with the existing design shown on the left. It has two independent blades that attach on a shaft. To help speed the process of chopping the food, our new blade assembly on the right has two more blades, which are added on the opposite sides of each blade piece. They are also slightly thicker to resist wearing down easily. This change doesn't add any new components that need to be manufactured, and the geometry of the change is just a mirror of what already exists.
The three main components in which there is a lot of variation in the manufacturing process include the motor, the food bowl size, and the blade assembly. These combined create about 3 different final assembly options. By moving the circlip in front of the motor in the manufacturing process, we are able to reduce the number of steps in which there is differentiation in the manufacturing process.
We conducted a manual assembly analysis of our product to determine the components which take the longest to assemble. The longest assembly times were the gear caddy at 65 seconds, then the base plate at 59 seconds, and then the motor at 26 seconds. The total assembly time for the original design comes in at 323.5 seconds at an assembly efficiency of 15.7%. Based on the assembly time, we determined that the gear caddy and base plate were suitable candidates for DFA redesign. Here's our quad chart. Components in green are subject to elimination, components in yellow are to be unchanged, and the components in red are subject to be redesigned in accordance with DFA and DfM guidelines. Because of the long manual assembly times on the gear caddy and base plate, we determined that they would be redesigned with the DFA guidelines, with the gear caddy as a module and the base plate as the platform. We chose the gear caddy as our first part and made several design changes, especially to the overall geometry of the design. These changes were for the ease of editing of the CAD model, but also play a role in the DFM criteria mentioned later in this presentation. The first DFA guideline we followed was DFA 10, Features for Easy Insertion. We augmented the CAD model to have male nubs on both surfaces so that they would insert into the female hubs on their adjacent parts. The two other guidelines were DFA 2, Reduce Fasteners, and DFA 5, Reduce Part Variety, which work in conjunction with each other. The original design required the gear caddy to be secured by 5 fasteners of various sizes. However, our redesign only requires 2 fasteners to secure to the motor casing for initial assembly, then will be secured when the base plate is attached. All fasteners are now uniform, and these changes have resulted in a total time savings of 43 seconds.
The base plate was simplified while still allowing for the same functionality. We have easier insertion features by adding female insertion hubs, which makes it easier to align the gear caddy and motor casing. We also reduced the amount of fasteners required to hold these two together. And finally, we reduced the amount of part variety, making it easier for assembly. This redesign saved us almost 61 seconds in assembly time, 27 cents for the gear caddy, and 4 cents for the base plate for each unit.
For the automated sub-assembly, we chose to optimize the blade assembly, specifically the top and bottom blades and the blade shaft. We chose this subassembly because of its long manual assembly time and that it can be Z-axis assembled. In order to achieve a reduction in automated assembly time, DFA strategies for automated assembly were used.
We also redesigned two parts for automated assembly, which are the blade shaft and the blades. The fastener count was reduced from 4 to 2, the slot cutout used to locate the part was removed, a second symmetric blade was added, and dowel holes were added for locating. These changes allowed us to use the same blade for the top and bottom and enhance the product for our secondary customer group. The blade underwent a heavy redesign as we noticed that parts could be consolidated while keeping the function the same. We combined the shaft extension with the main shaft and simplified unnecessary geometry to allow for easy tool access to the rivets. We also added a feature to the gear caddy plate to prevent it from nesting with duplicates of that part, and added geometry that made for easier insertion and alignment.
The results of the DFA process yielded us a savings of 35 cents on both the top and bottom blades and 31 cents on the blade shaft. Another place where money was saved was the incorporation of the blade extension into the blade shaft, bringing our total cost reduction to $1.81.
Ultimately, this redesign saved us a lot of time and money. As you can see, we're saving about $1 per unit in assembly cost.
After dimensioning the base plate and referring to the FCMM and assembly steps, it was determined that the tolerance should be 0.3 millimeters.
Our process selection for the base plate using ABS plastic concluded 3 different possible manufacturing options that would work for the base plate. At the end of the process, we ended up choosing injection molding for the manufacturing.
So for the redesign of the base plate, we used a couple DfM guidelines, being minimizing the wall thickness as well as keeping it uniform. We also added a draft angle and avoided sharp corners and gave the corners fillets. And so when you look at the part cost estimation, it was about $1.87 before, and then after our changes, it drops about 32% to $1.27. Now the product function doesn't change, but the cost is cheaper due to less processes and times from machines.
Based on the dimensions and the assembly steps that involve the blade shaft, as well as the FCMM, it was determined that the tolerance should be 0.1 millimeters.
For the blade shaft using 6061 aluminum, our process selection analysis concluded that machining was the only viable option in order to complete the manufacturing process properly.
So for the blade shaft, we first decided to use standard stocks and dimensions to make things more accessible and common. And we also designed the holes to tool shape and avoided long and narrow ones. And so when you look over at the estimation, before any changes, the amount was roughly $7 to $8 per part, and after, it was about $3 to $4 a part, causing a reduction of about 45%. Now, the product function has no change, but the cost is cheaper due to standard dimensions, and the manufacturing cost is cheaper due to less processes and times.
For the gear caddy redesign, we mainly focused on making everything a little bit more uniform. So we minimized the wall thicknesses where we could and made it a more uniform wall thickness throughout. We added a couple of draft angles and we had locators with ribs. And that we made sure the rib thickness was less than 60% of the wall thickness. And we avoided sharp corners, so we had fillets everywhere. As you can see, there was no significant change in functionality and also not a huge change in cost, but we did have a 2% cost reduction.
A good PSS for the food processor is providing resources for repair. This includes parts supplied by the OEM, such as replacement blade sets, as well as spec sheets and manuals for repair. Repairs reduce the environmental impact of the food processor since they use less resources and create less pollution than replacing the entire product. Most repairs cost less than replacing the entire unit as well. Providing this PSS is enforced in some places with right to repair laws, which require OEMs to provide parts and publicly available information for repairs. Using design for assembly and design for manufacturability strategies, the overall manufacturing cost of the food blender was reduced by $529, or 10.4% of the original cost. The redesigned parts are more durable and resistant to vibrations, and the overall product uses less material. Both the automated and manual assembly steps require less time and resources. If the redesign could be improved, it would consider manufacturing and assembly steps for electrical components, such as soldering and crimping wires, and it would attach the blade to the shaft without the use of fasteners.